So in this video here, we will study a simpler predator-prey model. And here's how the system look like. So X, I guess we're assuming grows exponentially. So a lot of food resource, I guess. But it's being attacked by the predator Y. The predator Y has its natural death, and it gets only food source from the prey. So this conversion rate from the prey mass to the predator mass is denoted by this term right here. And this is what we call a simpler predator-prey model. In fact, there is a better name for this. This is often called Lotka Volterra System. So in this system here, we have 1, 2, 3, 4. Okay, 4 different parameters. X grows exponentially, being eaten by the predator. Y grows from the food source X, and it dies naturally. So let's try to study this system. In terms of the outcome of the two species, okay, the predator and prey. What happened to the predator and prey in the long run? Will they coexist? What's going to happen? Okay, let's find out. Equilibrium points can be easily found out. There are two equilibriums, 0, 0, meaning both the predator and prey will die, will extinct. Clearly, x 0, y 0, the right side is 0, the left side is the right side is both zeros. For the first one, if you factor out x, okay, factor out x, you can clearly solve for a y value, which is a over b. For the second equation, if you factor out the y, you will get an x value, which is c over d. So those two constants clearly represents the equilibrium state where both species coexist. And notice how the equilibrium for y depend on how fast the prey grows. Depend on a. The larger a is, y will get more food resource. This equilibrium gets bigger. It also depends on how fast x is being eaten by y. The smaller b is, the larger the equilibrium is. So you can take a quick look at those. Equilibrium can also be found by finding out intersection between the x noclines and y noclines. X noclines simply set ax minus bxy equal to 0. So it turns out there are two straight lines. One is x equal to 0. The other one is y equal to a over b. So that's the so-called x noclines. Along those straight lines, okay, x prime will be 0. Okay, along those straight lines, x prime will be 0. Similarly, y noclines are y equal to 0 and x equal to this constant. So now I like to just use the noclines and try to roughly come up with the direction field. So this provides me some intuition how the system behave. X noclines are x equal to 0. In other words, the y-axis, that's the x nocline. And also y equal to a over b. So this is y equal to a over b. The y nuclines is y equal to 0. And notice wherever they intersect, all right, so these are equilibriums, okay? The x nucline and y nucline intersects right here. That's one of the equilibrium that we already found out. Another one is x equal to c over d. So they intersects right here. So that was our second equilibrium, which cut this one into 1, 2, 3, 4, four different regions, and I can clearly identify the sign for x prime, y prime, and come up with the direction field. Along this x nucline, okay, along this line here, this is the x nucline, okay, that's the x nucline. X prime is always 0, so you have to study y prime. You have to study the sign of y prime. So once again, the equations are this. I'm going to write it back here so it's easy for us to check it out. And notice here I factored the both sides out. So along this nucline, along this nucline here, y prime, okay, y prime. I'm going to check y prime. The y is always, positive. X is 0, okay. Notice x is 0. This is x equal to 0. So the sign of y prime, there's a negative c here. It's negative, so y prime is negative. Meaning the direction field will be pointing downward like that. Along this segment here, you can check the sign for x prime. X is positive, okay, x is positive. Y is 0, okay, y is 0 along this edge here. So x prime will be positive. So this is how the direction field looks like. Along this x nucline, this is another x nucline, y equal to a over b. You can check the sign for y prime, okay, y prime. Along this nucline, check the sign for y prime. Because in this component here, this part, negative c plus dx will be positive, okay, will be negative. Okay, this part will be negative. Y is positive. So that's why y prime will be negative. So you guys can check this out, okay? Check the sign for y prime along this x nucline here. So it direction field pointing downward. Along this one, check the sign for x prime. Check the sign for x prime, okay? It turns out to be positive. Up here, check the sign for y prime. Turns out to be positive, so it's pointing upward. Over here is pointing downward like that. Sorry, pointing to the left side. So in those different quadrants, you can check the sign for both x prime and y prime. So I let you guys do this by yourself, okay? Carefully check the sign on the right side. That turns out to be how the direction field looks like. So based on this simple diagram here, okay, based on this simple sketch here, I have a feeling that there is a closed orbit centered around this positive equilibrium. I have a feeling that the trajectory is not going to be approaching this positive equilibrium. I have a feeling instead of something that tends to this positive equilibrium, we actually have some periodic solutions, a closed orbit. But we can't prove this for sure yet. But graphically, that looks to be the case. In other words, based on the rough analysis of direction field, I think the conclusion will be for this simple predator-prey model, in the long run, you will have some periodic solutions instead of the solution will coexist at this equilibrium. So now let's look at the different techniques we have developed so far and confirm this conclusion, okay? Conclusion we're trying to come up with is only closed orbit. All right, that's something we're trying to come up with. So as usual, we can study the local behavior, all right, the local behavior by using Jacobian matrix. So you can easily calculate this. Partial derivative with respect to x, partial derivative with respect to y. So clearly, the most interesting point here is the positive equilibrium. So I like to plug that into the Jacobian matrix, where x being c over d and y is a over b. So you plug that in, this term turns out to be 0. This component is also 0. So the eigenvalue turns out to be pure imaginary. In other words, the real part is 0. The real part is 0. So you can go ahead and calculate this lambda here, okay? So when you guys look at the videos here, make sure you practice the parts that you're not so sure about. Check it out, okay? Check it out, because I can't go into too much detail. So what does that mean? That means the linearization technique is not going to work. Remember, linearization only applies when the eigenvalues turns out to be has a real part that's not 0. So let's just say linearization technique does not work. Does not work. We cannot conclude anything about the stability. So next, let me try to create a Lyapunov function. Of the following form. So that'll help us to study the system. Okay, turns out for this system, a Lyapunov function that somehow we carefully created will be able to work things out. Now this is obviously very tricky. In general, creating a Lyapunov function is not something that's easy. Okay, it's not something that's easy. So that's something we need to create. So I'd like to take it to be in the following form. In other words, it's a pure function of x plus another pure function of y. Let's calculate the time derivative along the solution curve. I need this to be less or equal to 0. Remember, I need this to be less or equal to 0. Chain rule, differentiate this with respect to x, followed by dx dt. G prime dy dt. And then I plug in dx dt. Dy dt. So that's what it is. So my goal here is to create a Lyapunov function so that the time derivative along the solution curve is 0. Okay, it's 0. And notice this will be 0 if f and g satisfy the following condition. All right, so you can just set it equal to 0. You get x f prime. So group that and divide by this guy. Whenever they're equal, okay? Whenever they're equal. So once again, you can take this equation here and separate the terms so that the x terms are together, the y terms are together. So whenever they're equal, the time derivative will be 0. So why don't I just set this equal to set this equal to 1? Okay, like I said, as long as they're equal. So we set this equal to 1. That'll help us to find out capital F and capital G. So if I set this to be 1, here's the equation for F. F has to be, okay, I solve for F prime, and then I solve for G prime. So that's what the F has to satisfy, and this is what G has to satisfy. So here's the choice of capital F and G. So that the time derivative along this solution curve will be 0. Okay, will be 0. So we have the following choice. So basically integrate on both sides, get capital F, natural log of x. Thus, this function that we created, this Neopolo function that we created, which looks like this, that's f of x followed by g of y. This guy is a constant. Is a constant along the solution curve. So here, when we say this is a constant along the solution curve, we really mean whenever x and y satisfy the equation. Okay, whenever x and y is a solution to the system, then this guy is always a constant because the time derivative will be 0. Furthermore, let's look at the graph of f of x and g of y. Okay, they are separate. Here's f of x. F of x is dx minus c ln of x. The graph of this, okay, you can plot this. Turns out this guy achieves the minimal at this x naught. This is a pure function of x, so achieves the minimum at x naught equal to c over d. For those who are wondering why that is the case, well, you can just differentiate this guy equal to 0. Okay, you differentiate this guy. Remember, differentiate this guy, you get d minus c over x. Set is equal to 0. You solve for x, you get c over d. Okay, so that turns out to be the minimum point for f. The function g, okay, which is the guy back there, okay, this is the g here. Here is g of y. The y value, g of y also achieves the minimum at x naught, at y naught equal to a over b. And notice that is precisely the equilibrium points. That's the equilibrium points. So because f achieves the minimum at x naught, g achieves the minimum at y naught. So the sum achieves the minimum at this point and this point. So our conclusion is this Neopolo function has a minimum at the equilibrium point. So that's the equilibrium point. That's the equilibrium points. So I want you to go back to the part that we talk about the Neopolo function, and the results were different. Let me show you the Neopolo function we had before. And notice that for that part, I need L to be positive, always positive, and L prime always to be negative. Then I can claim X star to be asymptotically stable. L prime is negative. And notice what happened in this case is our L prime, okay, our L prime is always 0, okay, it's always 0. So that's very different from the results that we presented before. If L prime is negative, then the equilibrium will be asymptotically stable. So notice the different story here, okay? The L prime here is 0. And moreover, L has a minimal at the equilibrium. So what do we get out of this? And that's something we would like to clarify, okay? What do we get out of this? So we would like to present this as a simple theorem. Every solution of the model that we presented, or the Lotka Volterra model or system, every solution is a closed orbit. Okay. So let's look at the Neopolo function that we created before. All right, it has two properties. Number one, time derivative is 0 along the solution curve. In other words, L is always a constant, okay, whenever x and y satisfy the system. In other words, when x and y are solution, L will be a constant. Second property is L has a minimal at x naught, y naught. So those are two things to keep in mind. So let's try to make a simple proof here. I know we didn't do too much proof, actually not too much proof at all. So this gives you a little bit flavor, okay? This gives you a bit of flavor. So geometrically, that is the equilibrium point. I like to call this Z, okay? I like to call this point Z. So you start with any point W. I want to show you that this trajectory will not approach Z. Instead, it'll become a closed orbit. And that's what we're trying to prove here. So we denote the trajectory coming out of this initial data, or starting from W by. So this is a curve that depends on time, obviously. So we simply denote it by phi of time, phi of t. Also depend on where you start. Based on our analysis, we know that this guy will cross this node line somewhere, and then cross this guy somewhere, and then furthermore cross this one somewhere else. So let's say there exists different times such that this trajectory at those time, okay, this trajectory at those time will be on the x node line. So this is time t1, and if you try to approach Z, it'll cross the node line again at different time t2, and so on. It's on the x node line. And as the Tn goes to infinity here, this trajectory is monotonically increasing along this line, okay, because the value is getting bigger and bigger, the y value is getting bigger and bigger. So this is monotone increasing along this line. Along this line. And thus, it'll approach z as n goes to infinity. Of course, we're trying to show this is impossible. Okay, we're trying to show this is impossible. Let's find out what is the contradiction in this statement here. Okay, so here we're saying if phi does approach z, that'll be the way it approaches, right? There are different times where the trajectory keeps getting bigger, getting higher and higher, and eventually approaches z. So now let's look at the Neopolo function that we created. This Neopolo function is always a constant along this trajectory. It's a constant. The reason is because the time derivative is 0. Remember, we proved this. So it's a constant along the solution curve. So at any point, okay, it doesn't matter where it is, L is always a constant. So here's what we have. The Neopolo function at W, okay, W which is your starting point on the solution curve, it'll be the same value as the Neopolo function value at the limit point z, if you are assuming this goes to z. Well, what's the contradiction? Well, the contradiction is the fact that L that, as we proved, has a minimum at z, has the minimum at equilibrium. So this contradicts the fact that L achieves the minimum at the equilibrium z. So the contradiction comes from from our assumption that this trajectory is not a closed orbit. Instead, it keeps crossing this x0 line, getting closer and closer to z instead. So that's where the contradiction comes from. And that's how we conclude that the trajectory or the solution curve must be a closed orbit. Okay. So here we created some sort of a Neopolo function. We use it to show that the solution to the Lotka Volterra system has to be periodic. Okay, has to be periodic. Our next topic will be chapter 12, some bifurcation theory. Okay, bifurcation theory, and that's the last topic we're going to talk about.